In this PowerPoint, we'll discuss how you can use the ideal gas law in stoichiometry calculations using a balanced chemical equation. Because the ideal gas law includes moles as part of its basic formula, we can convert into the moles of any gas as long as we know the pressure, volume, and temperature of that gas. In the same way, we can convert out of moles, if we know that, of a gas, into either pressure, volume, or temperature. And this fits very well with our stoichiometry calculations, which all rely upon, at their heart, a conversion of moles of one substance into moles of another substance, using the coefficient ratio from the balanced chemical equation. Let's look at an example. An acetylene tank for a welding torch provides 9,340 liters of acetylene gas at 0 degrees Celsius in 1 atmosphere. How many liters of oxygen gas are required to burn the acetylene? And we're given the balanced chemical equation for the combustion of acetylene. So the first step in any chemistry problem is to define what we're given. We have a volume of acetylene gas, a temperature, and a pressure. And we're asked to find the volume of oxygen that reacts with this. So this is a stoichiometry problem, and we have two different substances. We can define our given substance, acetylene, as A, and what we're trying to find, oxygen, as B. And we know that the heart of any stoichiometry calculation is always the conversion of moles of A, what we're given, to moles of B, what we're trying to find, using the ratio of coefficients from the balanced chemical equation. Now this is the heart of the calculation, but before we can do that conversion, we do actually have to get the units of what we're given into moles. So we have to do a conversion. And because acetylene is actually a gas, we can use the ideal gas law to convert from volume into moles. So we'll use the rearranged form of the ideal gas law to solve for moles, N, pressure times volume divided by the ideal gas constant divided by temperature. We just have to make sure that everything is in the correct units. So volume is in units of liters, pressure is in units of atmospheres, temperature does have to be in Kelvin, so we add 273.15 degrees to it, and of course we also need the ideal gas constant. We substitute all of these into our equation, and notice what happens to the units. Atmospheres cancels with atmospheres, liters cancels with liters, Kelvin cancels with Kelvin. We'll be left with moles. We can take this moles of acetylene and then apply our next step, which is the conversion using the coefficient ratio. So 416.69 moles of acetylene times 5 moles of oxygen, which is the coefficient from the balanced chemical equation, divided by 2 moles of acetylene, also from the balanced chemical equation. Our moles of acetylene cancel out. We'll be left with moles of oxygen. And our last step is to actually convert from moles of oxygen into the unit we're asked for in the problem, which is volume. And again, oxygen is a gas, so we can use the ideal gas equation to do this. We just rearrange it to solve for volume this time. So this is going to be moles N times the gas constant times temperature divided by pressure. And we already have our moles, our N term right here, so we can just multiply that by R, our ideal gas constant, times the temperature, and divide it by the pressure. Again, our units cancel out, moles divide with moles, atmospheres with atmospheres, Kelvin with Kelvin. We're left with units of liters. And we can round this value, 23,350 liters, into 3 significant figures to match the 3 given in all of our starting variables. And it's 2.34 times 10 to the 4th liters of oxygen. So I solved this particular problem in 3 separate steps. And you may not have been able to see it in the stepwise calculation, but an interesting thing actually happened with the temperature, pressure, and ideal gas constant as we worked our way through the calculation. So I'm going to show you this calculation again, but this time with all the steps combined, so you can see more clearly what happens to these particular variables. So we could also write out our calculation in one long equation instead of 3 separate ones. And this is what it would look like. It's all the same math, though. It's just written together. So the first step we did was to convert liters of acetylene into moles of acetylene by multiplying our volume times the pressure divided by the ideal gas constant and divided by the temperature in Kelvin. That gave us moles of acetylene. We then took the result of step 1 and multiplied it by the coefficient ratio from the balanced chemical equation in step 2. And we took then the moles of oxygen that we got from this conversion and applied that to our volume calculation for oxygen by multiplying by the ideal gas constant times temperature and divided by pressure. And this was our step 3. So this doesn't show each individual step answer along the way, but the math would be exactly the same. And this form makes it a little bit easier to see what happens in terms of pressure, ideal gas constant, and temperature over the course of the entire calculation. We have 1 atmosphere of pressure on top here and on the denominator in our last step. That's going to cancel out. The ideal gas constant in the denominator in the first step cancels with the ideal gas constant in the numerator in the last step. And the same thing with temperature. And it turns out that you could actually get this exact same result if you had just taken our original volume of acetylene and multiplied just by that coefficient ratio, 5 moles of oxygen divided by 2 moles of acetylene. And this is a much simpler calculation. This leads us to an interesting variation on stoichiometry calculations for gases. When pressure and temperature are held constant throughout a reaction, the volumes are directly proportional to the moles of the gases involved. This is actually Avogadro's law, one of the simple gas laws. And it allows us to interpret our stoichiometric coefficients with units of volume, or liters, as well as moles. And so this is actually a better way to write our simplified calculation for this problem. The coefficient ratio, instead of being 5 moles over 2 moles, is actually 5 liters of oxygen over 2 liters of acetylene. And we can see that liters of acetylene cancel out, and we're going to be left with liters of oxygen. Now, it's really important to note that this shortcut will only work when pressure and volume are constant throughout the reaction, and you are converting from volume of one gas to volume of another gas. So if you must convert between a solid or a liquid and a gas in a chemical reaction, then you have to do the full calculation using the ideal gas law. And here's an example. Sulfur dioxide, SO2, is an intermediate in the preparation of sulfuric acid. What volume of sulfur dioxide at 343 degrees Celsius and 1.21 atmospheres is produced by burning 1 kilogram of sulfur and oxygen? All right, so we're given as our starting amounts the mass of one of our reactants, and it's a solid reactant. We're also given temperature and pressure. Temperature and pressure won't really affect the mass of a solid, but they will influence the final volume of our gaseous product, sulfur dioxide. So this is what we're asked to find. We start with sulfur, which is our A, and go to sulfur dioxide, which is our B. And since we're starting with a mass, we have to convert mass first to moles of sulfur, the heart of our stoichiometry calculation, using the molar mass of sulfur. Then we use the coefficient ratio between sulfur and sulfur dioxide to convert to moles of sulfur dioxide. And finally, we calculate the volume of sulfur dioxide using the ideal gas law. So because we're using the ideal gas law, our units have to be in the appropriate form. So degrees Celsius has to be converted to Kelvin. And we need to also include the ideal gas constant, our 0.08206 liters times atmospheres divided by moles divided by Kelvin. So we'll start with our mass of sulfur. And it's actually in units of kilograms, so we need to convert that into grams. So there's 1,000 grams, or 10 to the third grams, in every kilogram. So we divide by the kilograms and multiply by 1,000 to get our grams of sulfur. We then convert into moles of sulfur by dividing by the molar mass so that grams cancel out. And we also, for our second step, convert that to moles of sulfur dioxide using our 1-to-1 coefficient ratio from the balanced chemical equation. Moles of sulfur will cancel out. We'll be left with moles of sulfur dioxide. Our last step will be to convert into volume. And so we can rearrange the ideal gas law to figure out what we need to do. It's moles times R times T divided by P. So we know that we have moles from the last step, so we can just multiply this by R and T and divide by P. Now in terms of my units, the moles in sulfur dioxide will cancel out, my Kelvin will cancel out, and my atmospheres will cancel out. So I'll be left with final units of liters. Notice that because I'm not dividing by 0.08206 in the first step, the number for the ideal gas constant does not cancel out, nor does the temperature, since I'm not dividing by that in the first step, nor does the pressure, since I'm not multiplying by that in the first step. So those numbers have to be included in our calculation this time. So we multiply by everything on top, divide by everything on the bottom, and we get 1,303 liters, which we can round to 3 significant figures, reflecting the number of significant figures in all of our original measurements. In summary, the ideal gas law can be used to convert into and out of moles of a gas, given pressure, volume, and temperature, for stoichiometric calculations involving reactions with gases. And if we're converting from volume of one gas to volume of a different gas in a reaction at constant pressure and temperature, the stoichiometric coefficients can be interpreted in units of volume, an application of Avogadro's law.